welcome everyone to this Forge College Explainer. I am absolutely thrilled to guide you through what is, honestly, essentially the engineer's blueprint for the entire Web3 world. So today we're looking at the historical motivations for the Bitcoin whitepaper. Human history is full of brilliant inventions that were born out of spectacular and sometimes kind of hilarious failures of trust. If you've ever handed your lunch money to a friend who promised to buy you a sandwich, but somehow they came back with only half a sandwich and a very unconvincing story, well, you understand intermediary failure. Right? Now, just multiply that sandwich by the entire global financial system, and you've got the exact historical stage that was set right before Satoshi Nakamoto published this famous document. We aren't just going to look at the math today, we are going to look at the why. Okay, here's the blueprint for today's explainer. We're going to cover 1. The crisis of trust. 2. The double spend problem. 3. Linking with hashes. 4. The 3-step workflow. And 5. Key design principles. Let's jump right in. Section 1. The crisis of trust, macroeconomic shocks. So to really understand the technical design of Bitcoin, we have to travel back a bit to the late 2000s. This was the time when the traditional banking system was under severe stress. Pre-2008, you had traditional banks acting basically like these massive, opaque black boxes. Money went in, but nobody really knew what kind of risk was building up inside. And then bam! 2008 hits, the black boxes break open, and they look less like secure vaults and, well, more like shattered piggy banks. We saw massive, highly visible failures of trusted financial intermediaries. We're talking bailouts, frozen accounts, just total panic. Now, this isn't just historical background color. This is literally the exact pressure cooker that created the post-crisis demand for decentralization. People started asking a really radical question. Is it actually possible to have a financial system that simply doesn't rely on a centralized authority not to lose our money? Which brings us to Section 2, the double spend problem, core technical hurdle. Okay, so if you want to bypass the banks completely, you run into a massive engineering wall almost immediately. Think about physical cash for a second. If I hand you a crisp $20 bill, I don't have it anymore, right? You have it, it's physical. But digital money is really just data. It's just a file on a computer. And what is the absolute easiest thing in the world to do with a digital file? Copy and paste. Without a central bank sitting in the middle, updating some master spreadsheet, what exactly stops me from writing the exact same digital $20 check to Alice and also to Bob at the exact same time, and just kind of hoping they don't compare notes? That right there, that's the double spend problem. So we arrive at this pivotal question. How do we fix the double spend problem without a bank? If we literally can't rely on a single trusted entity to sit in the middle and reject the duplicate transaction, we need a network of complete strangers to somehow agree on who owns what and in what exact order the transactions happened. And this is where the magic transitions from just a historical complaint into a really elegant engineering solution. Section 3. Linking with hashes. Minimal blockchain. Let's look at the technical schematic right here on our drafting paper. We are going to build a minimal Python blockchain together right now. Just think of this basic block class as like a mechanical locking mechanism with 4 main components. First up, we've got the index, which is just its position in the chain. Simple enough. Second, the data, which is our payload, something like Alice pays Bob 5 coins. Third, and honestly this is the star of the show, the prev_hash, or previous hash. This is a cryptographic pointer to the block that came right before it. And finally, its own hash, which is its unique identifier. So by giving every single block a fingerprint of the previous block, we are physically locking them together in a specific, totally unchangeable order. Now, let's look at the compute_hash function to see how this actually builds our locking mechanism in the code itself. It takes the index, the data, and that previous hash, squishes them all together into a string, and runs it through a cryptographic algorithm called SHA-256. Think of SHA-256 like an industrial-strength wax seal. It securely binds all this information together into a totally unique, fixed-length string of characters. If you go in and change even a single comma in the data, the entire hash changes completely. And the absolutely crucial point here lies in that previous hash. In a valid chain, every block's prev hash perfectly matches the actual hash of the block before it. But let's simulate a double spend attempt on a tampered chain. Say someone gets a little greedy and tries to change an old transaction in block 1 from 5 coins to 50 coins. What happens? Well, because the data changed, block 1's new hash is totally different. But block 2? Block 2 is still pointing to the old hash, so the link is completely broken. That hash mismatch instantly acts like a blaring alarm system for the entire network.
The tampering is immediately evident to everyone. No way around it.
Moving on to Section 4, the three-step workflow, mapping motivations. All right, now that we've seen the micro-level locking mechanism in action, we need a way to zoom out. We need to apply this when reading the actual Bitcoin white paper. And I highly, highly recommend using this standardized pedagogical framework when you dive into Satoshi's text. It just makes everything click. Step 1, identify the historical pressure, just like we did with the banking crisis. Step 2, ask what specific security property is needed to relieve that pressure. And step 3, match that to the actual mechanism proposed in the white paper. By doing this, instead of just reading dry technical specs, you are actively translating real-world complaints into concrete cryptography. Let's actually put that workflow into action. If the historical motivation was, say, distrust of intermediaries, the mechanism Satoshi chose was a replicated public ledger. And the practical effect of that, it completely removes the need for a single trusted custodian. Boom. What about the double spend risk? Well, the mechanism there is proof of work and the longest chain rule, which objectively resolves transaction conflicts without needing a referee. And for censorship risk, the mechanism is a permissionless broadcast network, meaning literally anyone, anywhere can propose a transaction. So, as you can see, every single line of code exists to solve a very specific human problem. Section 5. Key design principles, knowledge wrap-up. Okay, here are your core takeaways for today. First, the design of Bitcoin is entirely problem-driven by those trust failures of 2008. Second, making a ledger tamper-evident requires those cryptographic hash pointers we looked at in Python. But third, and definitely pay close attention to this one, guys, while hashes detect tampering, deterring an attacker from just recalculating the whole chain requires a massive economic cost. That is exactly why proof of work exists. It makes rewriting history just impossibly expensive. And fourth, always read the white paper through the lens of these motivations. I want to leave you with this provocative thought to kind of guide your future learning. When reading the white paper, ask yourself, what historical failure is this mechanism engineered to prevent? If you just keep that single question in mind, all the technical jargon turns into a really fascinating story of problem solving. Thank you so much for watching this Forge College Explainer. I really hope this gave you a solid, engaging foundation for your Web3 journey. Now, to learn more about this subject, dive a lot deeper into the code, and explore all of our other Web3-related topics, please visit our website at forge.college. Keep exploring, and I will see you in the next one.